Hello, my lovely students. So we are looking at section 3.4, which deals with, it says, derivatives as rates of change. What this really is dealing with is we're going to focus in on functions that map position versus time. So let's dig in and take a look. So just basic ideas here. When we talk about velocity, that's a fancy physics word. That is the change in position over the change in time. So that's some distance divided by some time. Usually this is like, how fast does your car go? 60 miles per hour. And if you're in the left lane, people get mad. Acceleration is the change in the velocity over the change in time. So you might be going 60, but are you going 60 with your foot pedal to the metal? Or are you going 60, but you're slamming on the brakes? Are you speeding up or are you slowing down? Or you could have no acceleration at all. You could cruise at 60 with no change if you set your cruise control. So here we have a graph. This is time in hours versus distance traveled. So the distance is miles, the time is in hours. So what is the slope of this graph? So we can literally calculate this. And if I look for what I call a nice point, I see over here 5 correlates with 300 miles. So this is the ordered pair 5, 300. And then of course I can see at time 0, we start at 0 miles. That's a very normal starting condition, especially in physics classes. So slope, because we're looking between these 2 points, old school slope is just rise over run, change in y's over change in x's. Our y2 is 300. Our x2 that goes with it is 5. And then our y1 and x1 were zeros. So I end up with 300 divided by 5, which is 60. Now the follow-up question is, what are the units here? So when I look at my 300, 300 is a y number, y is distance in miles. So this is not just 60, but this is 60 miles divided by 5 is an x number, which is time in hours. So this is miles per hour. So this is how long the car was driving, how far the car went, and then the slope that we calculated, the change in the y values is distance, the change in the time values is time in hours. We ended up with 60 miles per hour. So the slope of the distance graph is the speed being driven. Now, since the distance shown here was just a nice straight diagonal line, this is a position graph for something that is moving at a constant speed. So this is like somebody was already driving on the highway, like driving, I guess, here to El Paso, because that's, you know, the most boring drive. So you just start driving west, and once you're outside San Antonio, there's not much there that's going to slow you down, probably. So you might actually be able to consistently stay at 60 miles per hour for 5 hours. I hope you have a good audiobook because the radio craps out at some point. But this tells us when we have this distance function, the input is time, the output is how far we've gone, the slope of that graph is the speed, the velocity. Now, those two words are not exactly the same. We're going to focus in on that in a second. But overall with our graph here, slope of the graph is velocity. Now, what about this one? We have a rubber chicken is chucked off of a roof. So suppose the y-axis represents the velocity in meters per second, and the x-axis represents seconds. So after 1 second, the y value is -10 meters per second. Now, what is the slope of this graph, and what are the units of that slope? Now, this is even more interesting. So let's pick some points. So here I have an input of 1. I have an output of 10, just like I said. And of course, I see this starts at 0, 0. So let's run through our slope calculation. Change in y's. So one of my y values is -10. The associated x value is 1. Then my minuses, and then my 0 over 0. So I get -10 is my results. Now, let's focus on those units. So the units on the y value are meters per second. So this is meters per second divided by my units on the bottom. My x values were in seconds, time in seconds. So this is meters per second per second. So we actually typically represent this as -10 meters per second squared. And meters per second squared, the rate of change of velocity, is acceleration. So this graph over here was the graph of time versus velocity. And the slope of the velocity graph here is the acceleration. So as more time passes, the chicken is moving faster downward. The acceleration being applied to the chicken is constant, though, because the slope of this line is constant. And -10 meters per second squared is roughly gravity. Gravity on Earth is -9.8 meters per second squared, so took a little liberty and rounded it so the numbers look pretty, but yeah, this is a chicken just being dropped. So slope of velocity is acceleration. Now remember though, slope is just a fancy code word for derivative. So slope represents a rate of change. So if a graph represents an object's position over time, or sometimes we'll say distance traveled over time, the rate of change of that graph will be velocity. And then if a graph represents an object's velocity over time, the rate of change of that graph would then be the acceleration. So now that we know how to find rate of change and we have our shortcut rules, now we can actually start looking at some of the same formulas that are presented in physics. And in physics, they give you like 8 formulas, and they say, if you know calculus, you wouldn't have to memorize all this crap. And they're right, because if you know calculus, you just need the first formula and you can derive the rest of them. And I use the word derive quite literally because they are derivatives. Now, we do want to talk overall the difference between average velocity versus instantaneous velocity. So the average velocity is the total distance being traveled divided by the total time being traveled. So when I look at my graph here, it's -x squared plus 9. So we're saying a ball is being dropped from a window 9 feet in the air. Its position as it falls is shown on the graph to the left. So this means as time progresses, the ball gets closer to the ground. So this is not saying that the ball is arced away from the building. Certainly there is a way to get the ball to fall that way. But what we're doing instead is we're dropping the ball from a building from 9 feet in the air. And then we're like taking a video, and then we're clocking the time of the video and the position of the ball as it drops. So we can look at my timestamp on the video is what position for the ball. And then I fast forward a little, my new timestamp is what new position for the ball. So the more time, the closer to the ground. When we look at this graph at 3 seconds, because that's our input number, that's what we assume usually, the output is at 0. So in 3 seconds, this ball hits the ground. Now, 9 feet is not very tall. 3 seconds, 1, 1,000, 2, 1,000, 3, 1,000. That's a very slow drop. But slope of the secant line. So the secant line is our start versus our end point. So the start of this graph is 0 for the input, 9 for the output. The end of this graph is 3, 0. So my slope of the secant line is, I need to put one of the points first. It doesn't matter which one. So I usually pick the one on the right as the first one. So my y value is 0, my x value is 3. Then I put my minuses. Now my y value is 9 and my x value is 0. So 0 minus 9 is -9. 3 minus 0 is 3. So I have a slope of -3. So that slope is the change in position, a distance, over the change in time. So our distance, they did tell us it was 9 feet in the air. So this is feet per, and they don't actually ever tell us the time, so we'll assume seconds. But -3 feet per second, that is the average velocity. So that is, on average, how far the ball was moving per second for it to land on the ground after 3 seconds. But if you look at the actual position, it looks like it starts kind of slow because after the first second, it hasn't gone very far. And then from the first to the second, it's gone further. And then from the second to the third, it goes even further. So it doesn't appear to be traveling at the same speed. It starts off slow and then gains speed. So what does this slope represent? This is the overall average speed of the ball. Over the 3-second interval we were looking at. So that's why that ... diagonal straight line is in there. That's the slope we just calculated. But the follow-up question is, all right, that's average velocity, but you didn't do a derivative, Dr. Liz, what's up? Well, that's because we're going to do it down here. So we've got its position function, and now it's asking, how could we find out how far the ball was moving exactly when it hit the ground? So not the millisecond after it hits the ground, because once it actually hits the ground, it stops. But just before, if we had a sensor that could register how hard it hit the ground, or we could clock it with a radar gun, how fast is the ball going right before the ground stops it? That's what we're going to figure out. So instantaneous velocity is the slope of the tangent line. Because remember, it starts out with no velocity because we're not throwing the ball, we're just dropping the ball. So when it drops, we're not adding a velocity, we're not pushing it down faster, we're not throwing it up to slow it down. We're just opening our hand and letting gravity take over. So that initial velocity at the top of the curve is 0. And if you look at the curve, the top of that curve is the vertex of a parabola. It's a flat line up there. So our slope, our derivative at that point should be 0. So now it's asking a more interesting question. What's the slope at the end? How fast is it going when it hits? So we're going to do the derivative at an input of 3. Because that is when the position is 0. So that's why we're putting in 3, because it's 3 down here. So I've got my function. So I'm going to go ahead and find my derivative. So f prime of x, My f of x is negative x squared. So my derivative of negative x squared and then plus 9, the derivative of negative x squared. We are going to have, I'm going to write that negative side as a -1, the negative sign, times the derivative of x squared. We bring the power down, 2 times, and then instead of the second power, it's now the first power, plus 9 is a constant, so the derivative of a constant is 0. So our derivative function, the derivative for any time, is -2x. So if I plug in my time number, this will tell me how fast the ball is going. Now in this case, the time that I want to know about is 3, so I'm going to put that in for x. So we're evaluating now f prime of 3. So that is -6 feet per, again, question mark on the seconds. Maybe we're on some foreign planet where the gravity is really slow, so maybe instead of seconds, that's minutes. Maybe it takes 3 full minutes for this ball to finally hit the ground. But if we assume seconds, then it's going downward. It's got a downward pointing velocity of -6. So the speed on the radar gun would be 6 if it's in seconds, feet per second. That is our instantaneous velocity. That is the average between our starting velocity of 0 and our final velocity of -6 averages out to that -3 we got for the secant line. So overall, when we are given a function, and for some reason they use the letter S. I don't know why. In general, when I don't make sense of the letters they pick, I generally blame the French. Like, I don't know why M is the letter for slope, but I blame the French. Just because a lot of very famous mathematicians were French and they wrote everything in French. So naming conventions like, I think it's like mountain instead of slope. So S is our position function. The derivative of the position function is the velocity function. The derivative of the velocity function is the acceleration function. So I've got several different statements in there. And then I've got this extra bonus statement for the word speed. So the speed of an object is given by the absolute value of the velocity function. So speed is always positive. Velocity actually has direction attached to it. Positive velocity is assumed to be moving forward. Negative velocity is assumed to be moving backwards. But the speed you are going is the absolute value of the velocity. So whether I'm going forwards or backwards, like if I'm going 60 miles per hour forwards, yay, I'm driving my car normally. If I'm going 60 miles per hour backwards, I hope something else is driving my car because I don't think my car can do 60 in reverse. All right, so we're going to play around with this now. We're going to see some weird examples. All right, so we have some colors, and then we have some other colors that don't match with the colors being written. So bear with me on the weird colors. So we have a red car traveling along a highway with a velocity of 60 miles per hour. A blue car is traveling the opposite direction with a velocity of -80 miles per hour. Which car is moving faster? So I got pink car. He's going 60 miles per hour. We'll say to the right. Then I've got blue car. And blue car is going negative 80 miles per hour to the left. So right versus left, that's why the left one is negative, because it's the opposite direction from the right one. Now, which one is moving faster? That question is actually a very misleading question in math land, because we're like, what do you mean by faster? In this case, the assumption is we mean which one has the bigger speed. So which one is like objectively going faster might be a way to kind of English word think about it. So I would say my speed for the blue car is the absolute value of negative 80 miles per hour. So that is 80. My speed of the red car is the absolute value of 60 miles per hour. So that is only 60. So which car is moving faster? Blue. Now, if the question was which car is going to get to a particular location first, that depends on where the location is. But just a strict overall who's moving faster, we just care about what the speed is, not which direction they're going in. So we strip away those negatives to talk about speed. Now we're going to have to keep this idea of positive versus negative is which direction we're going. Size of how fast we're going, that's where our speed is going to come into play. Now, another thing that can come into play here is this idea of displacement versus distance. So let's read the scenario. Suppose you're walking along the street. So you walk 50 meters up the street. So let's say like you're on the sidewalk and you're like, I'm hungry. You walk 50 meters over to the McDonald's. You get your food. Then you turn around and you walk 70 meters back. So how much total distance did you travel? If you had, you know, your Fitbit, your step meter on, how much did you go? So our total distance is 50 meters plus 70 meters. We don't care about the direction when we're talking about distance. So if I'm counting my steps, I walked 120 meters. I got good steps in. But the other question, displacement, is a question about where did you end up relative to where you started from. So let's actually draw the picture. All right, so we're starting. We're going to go 50 meters over, you know, to our golden arches. And then we turn around and we walk in the opposite direction. So now I'm going to walk this way 70 meters. So how far am I from where I started? So I went 50 meters right, and then I turned around and I went 70 meters left. How far am I from where I started? I'm only 20 meters from my start. So my displacement is 20 meters. I mean, in our picture, we would say left of start, I guess. But it all depends on how you orient the picture. Maybe it was north and south. So we have to be careful about when we have signs on something that indicate direction, how the numbers interact and how we want them to interact changes based on the circumstances we're talking about. So if I just want to know where did I end up, I have a positive 50 and a negative 70. I add those together, I end up at negative 20. 20 in the negative direction from where I started. If I want to know how much walking did I do, I'd do 50 meters plus the absolute value of negative 70, which would be 70 meters, for a total of 120 meters. So it really just depends on the question being asked. Now, think about this weird situation. Suppose the velocity of an object is negative 20 meters per second, and the acceleration is 20 meters per second squared. So we have a direction being implied in both of these terms. So the velocity is negative. So if I think about like my little car, the velocity is negative 200 meters per second. The acceleration, though, is positive 20 meters per second squared. So, I don't know, maybe this is like on a track or something, like a little toy car. It's going backwards at negative 20 meters per second, but there is a forward acceleration pulling on it. So which direction is the object moving? It's moving in the direction the velocity says. It's being pulled backwards. Which direction is it accelerating? The acceleration is forwards. So now the question is this speeding up or is this slowing down? So if I have a negative velocity, I'm being pulled backwards. So like maybe I'm in a car and there's a rope with a giant pulling me back, like trucking along, running at 200 meters per second. And I start accelerating. I now am trying to push my car forward. Those are conflicting forces. They're going in opposite directions. So they're going to impact against each other. So that giant is hauling ass and pulling my car, but I am making it more difficult for him. So by pushing down on my gas, by trying to apply an acceleration forwards, I slow down the overall progress. So is this speeding up or slowing down? This is slowing down because the velocity and acceleration are going in opposite directions. Now, if we had the reverse, a positive velocity and a negative acceleration, which might make more sense, I'm cruising along and then I have a fancy car and I deploy a parachute behind me. The parachute applies a negative acceleration. It starts dragging my car. So that will overall slow my car down. So if the two directions, your velocity direction versus your acceleration direction, are opposite, you are slowing down. And that's what our next slide is covering. So in general, when we talk about positive versus negative, we have to choose a direction for these. Usually what we end up choosing is we say, if the velocity is positive, then we say the object is moving to the right. We just needed to pick something, and on an XY plane, that's the positive direction on the x-axis, so that's why it ends up being that. So that means when the velocity is negative, then we say the object is moving to the left. So that's why I drew the diagram that way. If the sign of the acceleration matches the velocity, meaning they are both positive or both negative, then they're going in the same direction, so we're going to go more. So then the object is speeding up. It's going to get faster, go more. Now, if the sign is opposite, so that means one positive and one negative, and it doesn't matter which one is which, that is the situation where we say we are being slowed down. So we have to pay attention to, are they in the same direction, both positive, same direction, both negative? All right, then we're either speeding up forward or speeding up backwards. So sometimes instead of right and left, we might also think of these as forward and backward. But if I'm going 60 miles per hour, but I start hitting my brake, the brake is applying a negative acceleration. They're in opposite directions, so I slow down. All right, so now we have an actual, and we're going to use this example on more than one slide, but we have a potato being launched from a potato gun. So this is very like children thing to do. So a potato is launched vertically upward with an initial velocity of 105 feet per second. That is not slow, that's pretty fast. So it's launched vertically upward from the top of an 80-foot building. The height of the potato in feet above the ground after t seconds is given by this quadratic function. So you can see the 105 shows up in there in the middle. The 80, our original position, shows up at the end as a constant. Because this function, the position is the height, and our initial height when time is 0 should be 80 because I'm at the top of that building. But what this is going to do is we're going to see that this graph, the potato goes up for a while, and then it'll come back down, and it's going to splat all the way on the ground next to the building. So we're not technically shooting the potato at an angle. It's more like we took our potato gun, held it right off the edge of the building, and pulled the trigger so it shot up. But that way, when it came down, it didn't hit the roof. It came down next to the building and hopefully didn't hit anyone on the head. So this first question is asking us for the velocity of the potato at 2 particular times, and then the corollary, what's the speed of the potato? So let's start with our position function. S of t is negative 16 t squared plus 105t plus 80. Our velocity function is the derivative. So v of t is s prime of t, and now we're going to take our derivative. So the derivative of negative 16t squared is negative 16 times the derivative of t squared is 2t, and then to the first power, plus, then we have 105t, so that's 105 times 1t to the 0 power, plus the derivative of a constant is 0. All right, so I'm going to clean this up, and then we're going to plug in our numbers to figure out the velocity at these 2 times. So v of t is negative 32t plus 105. So I want to know what's the velocity at 0.5 seconds. So that'll be negative 32. We substitute in the 0.5. Sorry. And then we add 105. So that's 105 minus 16. I need to clear all that. That is 89. Velocity is feet per second. So after half a second, the potato is still going up. Now our velocity at 5.5 seconds, negative 32 times 5.5 plus 105. Now this should be negative. 5.5 seconds is much longer. So negative 32 times 5.5 plus 105. Yep, negative 71 feet per second. So there's our two velocities, 89 and negative 71. Our speeds, though, speed is the absolute value. So I clock the potato going 89 feet per second when it's going up and 71 feet per second when it's coming down. Both of the speed numbers are positive. So that's our difference in if a web work question asks you velocity versus speed. Velocity is whatever result we got from the derivative. Speed is the absolute value of those results. Now, our seeing potato is now asking us, while airborne, the height of the potato is increasing on what open interval and decreasing on what open interval. So increasing is when it's going up. So it's going up when the velocity is positive. And then decreasing is when is it going down? That's when the velocity is negative. So the point at which it changes between them is when the velocity is 0. So I'm going to rewrite our velocity function. It was negative 32t plus 105. So it starts at 105. Right after it shoots out of the gun, it's going 105 feet per second. It's positive, going up. At some point, the velocity becomes 0. So that is what we're going to solve for. We're asking, when is velocity equal to 0? So we're going to put a 0 in place of velocity, and we're going to solve for this time. So I'm going to minus my 105. So I have negative 105 equals negative 32t. And if you were a little worried about those negative signs, now you'll see, aha, they are going to cancel out. And then we just got to calculate what 105 divided by 32 is. And I don't think it's pretty. I think it's actually kind of ugly. Yeah, it is 3.28125. That is seconds. So from 0 seconds until 3.28125 seconds, the potato is going up. From 3.28125 seconds until it hits the ground, the potato is going down. Now, to actually answer this question, we actually need to know when does it hit the ground to actually fully write in the interval. But I can put in the starting interval. So I can answer, where is it increasing? It's increasing from 0 to 3.28125. Now this is both t numbers. This is t equals 0 and t equals 3.28125. Those are two input numbers on the x-axis. Now we're going to actually solve for, when does it hit the ground? And this solving is a little more annoying. because it hits the ground. Like technically you can think, well, when it's on the ground, the velocity is 0. This is true. But the function and the way the path and the graph works, that's not where the velocity equals 0. For the way the graph works, the velocity only equals 0 at the top of the path. The graph is only giving us all the information until the instant tiny millisecond before it hits the ground. Because we could use this same arc. If I dug a hole in the ground, then my arc would still be giving me the math for the rest of that. So if this was like shot off a building that it turned out ground level, there was still a basement in the building, like we could measure even further down. But when does it hit the ground? That's when is the position equal to 0? So we need to take the position function and set it equal to 0. So we have 0 equals negative 16t squared plus 105t plus 80. And to solve that, don't even try to factor it. It might, but I highly doubt it because our vertex number is not totally pretty, so I doubt this number is going to be that pretty. So I would just straight up quadratic formula this. So I'm using t equals because that's what our variable is in terms of. So negative b plus or minus the square root of e squared minus 4 ac all over 2a. Now there are two different numbers here, the positive square root number and the negative square root number. What I like to do first is calculate what's inside the square root. So 105 times 105 minus 4 times negative 16 times 80. So I have negative 105 plus or minus the square root of 16,145, all divided by negative 32. So that's just my numbers being simplified a little. And, you know, as per usual, I write too big, so let me give myself more room. So let's see what the square root, nope, not that. So yeah, the square root of that number is ugly. It's 127.06, blah, 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 blah. So I'm going to do negative 105 plus that square rooty number. And then I'm going to divide that by negative 32. So my first number is negative 0.6894, blah, blah, blah. Right, now I'm going to rewind. Negative 105 minus the square root of 16145 is negative 232 something, and now I'm going to divide this by negative 32. And I get 7.25196, blah, blah, blah. So if I was looking at this particular graph, first instinct is, what does that negative 0.68 mean? Like, we don't talk about negative time. So for a second here, I'm going to draw you a picture of this. So here is my bad building. There is my ground. Let's give the building a little window. So the arc of this path, if I'm plotting it out where t is how long it's been in the air, so that's what's along the bottom is. So at t equals 0, potato is at the top of the building. At 3.28 seconds, the potato is at the top of its arc. At 7.25 seconds, potato has finished its arc. Now this arc is still a parabola. Even though we know the potato itself didn't actually move left or right, if I plotted it in relation to time, I would get this arc. The other part of the arc, if I finished the graph, the other x-intercept, or t-intercept in this case, would occur at negative 0.68 seconds. So I can actually make use of that time and kind of work my way backwards and down to the ground and figure out, like, you know, how long would the potato be, like, all the way in the air if I fired from the ground instead of from the top of the building? Sort of. It doesn't exactly work that way, but there are times where you make use of that negative number. Most of the time, though, you just ignore it because it doesn't make sense in the context of this problem. We started time when we fired the potato in the air, so that negative number is just kind of dropped and ignored as extraneous. So to answer our question, it's increasing from 0 to the 3.28. So let me write that in the graph. This is where the height is increasing. And then on the other side, this is where the height is decreasing. We could also say the height is increasing when the velocity is positive, and the height is decreasing when the velocity is negative. So that point at the top, that is when our velocity is 0, when the slope of the tangent line is flat. And if you think about tossing a pen in the air, like it goes up, like pauses, and then comes down. That pause is technically an infinitesimally small point. It doesn't actually hang in midair. But there is a point when the upwards velocity is finally slowed enough by gravity that then it'll start coming down again. So that pause point is a 0 velocity. So our decreasing height, our decreasing interval, would be from the 3.28125 to the 7.25196. And remember, these are t numbers. These are intervals. The same way we say, what is the domain, the set of all permissible x values, and we used interval notation for domains. This is interval notations for increasing and decreasing. These are not ordered pairs. The 3.28 number and the 7.25 number are both times. The 0 number is also a time. It's 0 seconds. So a whole lot of information on this one. I'm going to stop the video here to take a small break, and then I'll record a second video to finish this off because there's a lot of meaty stuff in this, and it has a lot of good applications in physics.